Let's begin with Lecture 9 of Design of Seismic Resistant RCC Residential Building based on IS Code. In the previous lecture, we looked at the design of column. Our column is designed by the ETAP software itself. We just looked at some processes associated with the design of a column in ETAPS. We will continue with our design classes and see the design of foundation in this lecture. In foundation, since it is a typical residential building, a 2.5-storied residential building, we will be looking at the design of isolated footings, and we will first look at some general considerations regarding the structural design of isolated footing, and then we will look at the design of that isolated footing in Excel. We will see just a simplistic design of an isolated footing, and we will learn about the design of isolated footing in SAFE software in our upcoming lecture. So let's start with our lecture number 9, Design of Foundation. IS code has 1904 code, which is a code of practice for design and construction of foundation in soils. The IS code 1904 states some general requirements pertaining to the construction of foundations. And if we begin at the very beginning, or if we see, our foundation are generally of two types: shallow foundation and deep foundation. In shallow foundation, the load transference is primarily through shear resistance of the bearing strata. It is normally laid to a depth of 3 meters. Generally, shallow foundation means that type of foundation in which the load from the superstructure is transferred to the swale primarily through the shear resistance of the bearing strata. Bearing strata means that layer of the swale on which our foundation is resting, and our load from the superstructure is primarily transmitted to the swale through the shear resistance. Shallow foundation is normally laid to a depth of 3 meters. And another type of foundation is a deep foundation. A deep foundation transfers loads to a deeper load-bearing strata when no adequate bearing strata exists at shallow depth. That means if the upper layers of soil or the upper strata in our soil profile are not able to withstand the loads from our superstructure, then we have to design our foundation in such a way that our loads are transferred to the lower strata. And in such cases, we design deep foundation. The transference of load by a deep foundation may be through friction, end bearing, or a combination of both. You may have studied in your soil mechanics classes or design a foundation classes that piles are constructed. Piles, which are an example of a deep foundation, they are constructed to transfer the load from any superstructure to the soil, and those piles are able to transmit those forces to the soil through different medium, and that medium may be either through friction, end bearing, or a combination of both. So while shallow foundation transfers load through the shearing resistance, the deep foundation transfers loads through friction, end bearing, or a combination of both. And IS 1904 code discusses on this shallow foundation and deep foundation types. Continuing with what is stated in that particular code, that is our 1904 code, there are various conditions, or there are various points related to the design of foundation, and I have taken one particular point from that code. The depth of foundation depends upon the following principal factors. So what are the factors on which our depth of foundation depends on? And according to this code, our depth of foundation depends upon, first, the securing of adequate allowable bearing capacity. Our soil test report gives us the bearing capacity at various depths of the soil, and based on our soil test report, we design our foundation to be built at a particular depth depending on the bearing capacity at that depth. In the case of clayey soils, penetration below the zone where shrinkage and swelling due to seasonal weather changes and due to stress and shrubs are likely to cause appreciable movements. That means that soil on which our foundation rests or on our that soil on which our foundation is built should be stable. There should not be too much of shrinkage and swelling. And if any such soil is present in designing our foundation or in constructing our foundation, which mostly occurs in the case of clay soils, then our foundation depth should not be built at that place but rather to a different depth. So there should not be any appreciable movement either due to the property of the soil, that is shrinkage and swelling, or due to the presence of any trees and shrubs around. In fine sands and silt, penetration below the zone in which trouble may be expected from frost. And in case of rivers or in case of water-bearing structures, the maximum depth of scour wherever relevant should also be considered, and the depth of the foundation should be located sufficiently below this depth. And this factor number D is primarily a prominent factor during the construction of bridges. In bridges, we build different types of foundations, that may be well foundation or caisson foundation or any other type of foundation. And in the construction of bridges, the scouring depth of the river becomes an important factor. Our foundation of those bridges should reach to that depth which is greater than the maximum depth of scour by the river. And other factors such as ground movements and heat transmitted from the building to the supporting ground may also be important during the design and construction of foundations. So let's come to the structural design of isolated footings. Before actually going to our design part, our design portion in our Excel sheet, we will look at some of the conditions in our relevant IS code and other codes pertaining to the structural design of foundations. First, in clause 34 of IS 456 code, the code states about footings or foundations, and clause 34.5.1 says that minimum reinforcement and spacing in footings shall be as per the requirements of solid slabs. And if you remember, for solid slabs, the minimum percentage of steel in each direction is 0.12% if we are using high strength deformed bars or welded wire fabric. Also, the minimum percentage is 0.15% when we are using mild grade steel, that is FE 250 grade steel. So this codal provision of minimum percentage of steel, which is for solid slab, is also relevant for footings. For our footings also, the minimum reinforcement percentage is either 0.12 or 0.15 depending on the type of steel that we are using. The nominal reinforcement for concrete sections of thickness greater than 1 meter shall be 360 mm square per meter length in each direction on each face. This provision does not supersede the requirement of minimum tensile reinforcement based on the depth of the section. That means, based on the depth of our section, suppose we get a certain value of tensile reinforcement. And if that value of tensile reinforcement is greater than this 360 mm square per meter length in each direction, then we have to use that greater value. However, if that value is lesser than this 360 mm square, then the nominal reinforcement for concrete sections of thickness greater than 1 meter shall be adopted to be 360 mm square per meter length in each direction on each face. So our clause 34.5 states about the nominal reinforcement requirement in isolated footings. If we go to our clause 26, which has requirements governing reinforcement and detailing, clause 26.3.3 adds some codal provisions regarding maximum distance between bars in tension. And this provision, which is for slabs, is also relevant for footings. That says the horizontal distance between parallel main reinforcement bar shall not be more than 3 times the effective depth of solid slab or 300 mm, whichever is smaller. So in case of our footings also, the center to center distance of the horizontal reinforcement should be either 3 times the effective depth of that footing or 300 mm, whichever is smaller. So this 300 mm and 3 times the effective depth is the condition for main reinforcement, and for parallel reinforcement bar which are provided against shrinkage and temperature, that is distribution reinforcement, that in that case the distance between the bars should not be more than 5 times the effective depth of the solid slab, that means the footing, or 450 mm, whichever is smaller. So clause 34 talks about the percentage of reinforcement, and clause 26 talks about the spacing of that reinforcement. So continuing with the structural design of isolated footings, we have seen about the calculation of reinforcement or the minimum reinforcement. Now, what about the thickness of the footing? Clause 34.1.2 of the same IS 456 code again says that in reinforced and plain cement concrete, the thickness at the edge shall not be less than 150 mm for footings and soils, nor less than 350 mm above the tops of piles for footing on piles. That means, if we see our isolated footing, suppose this is our column and this is our isolated footing. We have two sloping sides and one horizontal side at the bottom. So our ground level is somewhere here. If we see this footing, what this clause says is that the distance at the edge of the footing, that means this distance, this edge distance should not be less than 150 mm for footings on soils. This is the minimum thickness that we have to adopt while constructing and designing the footings. Also, a leveling course of lean cement concrete. That lean cement concrete might be in the ratio of 1:5:10. That means 1 cement, 5 sand and 10 coarse aggregates, or 1:4:8 proportion of thickness 80 to 100 mm. That means from 3 inch to 4 inch thickness approximately is provided below the footing base, which serves as a separating layer between the natural soil and the footing, so that any harmful chemical present in the soil will not react with the cement concrete footing. That means we do not build this slab or this footing directly on our natural soil. What we generally do is that first we perform some brick soling or stone soling, whichever material is available on our site, and on top of that soling we construct a PCC, that is plain cement concrete, of thickness approximately 80 to 100 mm. And what does this PCC or this plain cement concrete does is that it bars the harmful chemicals that may come from below the ground surface and that may react with the materials of the footing. As we know that our footing is a structure lying inside the soil, and that so that we cannot subject our footing to regular maintenance. It is very difficult for our footings to be regularly maintained and regularly supervised. So we should protect our footing from all the harmful and abrasive reaction of the chemicals that may be present in the soil. And one way to do that is to construct a layer of plain cement concrete between the footing and the natural soil that acts as a medium that bars all the chemicals coming from the soil to the footing itself. Sorry. So what are the now let's come to the what are the considerations during the design of a footing? What should be checked, and what are the factors that determine the design of our isolated footings. We have to check for all these things: bending, that is bending moment, development length of reinforcement, one-way shear, punching shear or two-way shear, and the transfer of load from the column to the footing. One important consideration or design aspect of footing is that shear considerations predominate, and hence thickness of footing is governed by one-way or punching shear rather than bending. As a result, foundations are always under-reinforced. What we do during the design of footing is that first, we will determine the depth of our footing based on one-way shear, and we check for that footing using that depth of our footing for punching shear, that is for two-way shear and for bending moment. The predominant forces in our footing are shear forces. So we design for shear forces and then we check for bending moment. As a result of this, our foundations are always under-reinforced. So since shear force predominates in the design of our building, let us see at some shear design considerations. Shear design considerations. Clause 34.2.4.1 of IS 456 code states that the shear strength of footing is governed by the more severe of the following two conditions. So in clause A of this clause 34.2.4.1 and in clause B, the strength of footings is governed by the more severe of these two cases, A and B. In number A, we have one-way shear, and in number B, we have two-way shear, that is punching shear. So the more severe of these two shear forces is the determinant factor in the shear strength of footings and hence in the design of our footings. So what is one-way shear and what is two-way shear or punching shear? So what is one-way shear first? Consider that our footing is a wide beam. If this is the plan of our footing, let us consider that our footing is a wide beam because our width of our footing is larger compared to any normal beam. So if we consider the footing is a wide beam, the critical section is taken along a vertical plane extending the full width of the footing, located at a distance equal to the effective depth of footing from the face of the column. This is what is stated in number A. If we consider this as a wide beam, then the critical shear in this beam is located at a distance equal to a distance of small d from the face of the column. So if this is the face of the column and this is the plane that we are considering, then our critical shear lies in this plane, and this plane extends through the whole width of the footing, that is from here and here. So this plane is critical for one-way shear in our footings. The plane is at a distance of d from the face of the column, and this d is the effective depth of the footing. So if we look at our code, what this code says is the footing acting essentially as a wide beam with a potential diagonal crack extending in a plane across the entire width. The critical section. Let's look at this. The critical section for this condition shall be assumed as a vertical section. Vertical section means if we look at the section along this plane, then this is our vertical section. The critical section will be this vertical section located from the face of the column or pedestal or wall at a distance equal to effective depth of footing for footings and piles. That means this critical depth or this critical section is located at a distance of d from the face of the column. So this is one condition for determining the shear strength of footings, and this represents the one-way shear. Now if we look at number 2, two-way action of the footing, that means two-way shear or the punching shear with potential diagonal cracking along the surface of the truncated cone. or pyramid around the concentrated load. In this case, the footing shall be designed for shear in accordance with appropriate provisions specified in 31.6. I have specified this 31.6 here. What it says is that the behavior of our footing for two-way shear is identical to the behavior of two-way flat slabs supported on columns. So what are flat slabs? If our slab is supported only, suppose on our column, here is a column at the center, and our slab is supported only on the column without any beam, then this is an example of flat slab. What might happen in this flat slab is that if the punching shear or the two-way shear is excess, then this slab may fall through this column, creating a punching effect, that is creating a hole. It may happen that if this is our column, then our slab may just drop to the bottom. There may be just the predominant effect of punching shear. So our behavior of our isolated footing to the two-way shear is identical to this behavior of our flat slab. Our two-way shear in our isolated footing is not as critical as in flat slabs. Although the behavior is same, the degree of that behavior is not as critical as in flat slab, since our footing now rests on the swell. We have a support at the bottom to rest the footing. So where is this critical section for two-way shear? Our critical section for two-way shear is a perimeter. This perimeter section is our critical section for two-way shear, and this perimeter section is at a distance of d by 2 from the face of the column. Our one-way shear was critical only along a vertical plane, but extending along the whole width. So our one-way shear might be critical here or here, but our two-way shear is critical along this whole perimeter. So this is what is stated in clause 31.6 with respect to the two-way action of the footing. So we have to check for shear strength of our isolated footing on this vertical plane for one-way shear and on this perimeter section for two-way shear. So this is the shear design considerations for our footing. So let us see here, in one-way shear, the shear force to be resisted is the sum of the upward forces in the footing from the critical section to the edge of the footing. The consequent shear stress is given by this formula. So let us see here. This is our footing. At the center we have our column. And if we look at the plan of this footing, suppose this is the depth of the footing and this is our section, sorry, not plan, section. Our critical section for one-way shear will be at a distance of d from this face of the column. So what happens is that for this whole area, the shear force is due to the sum of the upward forces in the footing from the critical section. That means we may have upward forces here on this critical surface, and this shear force is to be resisted by the shear strength that develops in this vertical section. The shear force that acts on this critical surface due to the upward forces acting on this footing is to be resisted by the shear strength that develops in this critical section or this vertical plane. So our shear stress is given by the shear force divided by this B, which is the width of our footing, and D. D means the depth of our, or the effective depth of our footing. And in this figure, D is acting towards the inside of this plane. If we go from inside here, then through this inside our D is acting, and that B into D gives the area of that critical section or area of that section which resists the one-way shear. So this is our shear strength in the case of one-way shear. When shear reinforcement is not provided, the calculated punching shear stress at the critical section should not exceed K as tau Cp. where now this was the shear force or shear stress in the case of one-way shear. For two-way shear, our shear stress will be Vu2 by B naught into T. And this two-way shear stress should not exceed Ks tau Cp. This is also one of our codal provisions where Ks means 0.5 plus beta C, which should be less than or equal to 1, and tau Cp means 0.25 root under F Ck. So what is beta Cp? Beta Cp is the ratio of the short side to the long side of the column. So in the case of our square fitting, beta C will be equal to 1, and our value of Ks will be 1 plus 0.5 means 1.5, but since the value cannot be greater than 1, our value of Ks will be 1 itself. Fck is the characteristic compressive strength of concrete, and Vu2 is the punching shear force, which is the total upward reaction from the area bounded by the critical perimeter and the edge of the footing. So in one-way shear, we saw that our critical shear force acts on this area, but in the case of two-way shear, if this is our plan of the footing and this is our column, we saw that our two-way shear was critical at a perimeter section at a distance of d by 2 from the face of the footing. So our two-way shear acts on this area, this boundary area, and this area is limited by the critical perimeter section in the inside and the edge of the footing on the outside. So the shear stress or the punching shear stress in this area should be resisted by the shear stress along this critical perimeter section. So we were looking at the meaning of the values or meaning of symbols, and this B naught, where we have used here B naught, is the length of critical perimeter. That means this length of four sides, where C1 and C2 are the short and long sides of the column, and D is the effective depth of footing. So in this way we can calculate the shear forces in the case of one-way shear and two-way shear, and then we can determine the shear strength resisting those shear forces. And finally, in class 34.2.2, we just talked about a square column, which is very easy to calculate. But if our columns are circular or hexagonal, then what we do is that for the purpose of computing stresses in footings which support a round or octagonal concrete column or pedestal, the face of the column or pedestal shall be taken as the side of a square inscribed within the perimeter of the round or octagonal column or pedestal. Since our critical planes for one-way and two-way shear are based on this distance from the face of the column. In the case of our square column or any other different shaped column, it is difficult to find the face of the column. In that case, we choose an inscribed circular shape and we determine the distance of the critical section from that circular shape, or from that square shape, sorry, not circular shape, from that square shape. And finally, we come to the bending moment considerations. We only have to check for the depth which we have acquired from the shear configuration or shear strength considerations in the bending moment considerations. Our bending moment in our footing is critical at the face of the column itself. As we are looking at this figure and as we are seeing here, our bending moment is critical along the face of the column, along the plane containing the face of the column. The bending moment at any section shall be determined by passing through the section a vertical plane which extends completely across the footing, that means this plane, and computing the moment of the forces acting over the entire area of the footing on one side of the said plane. So, if this is the critical section for a moment, what is the critical moment here? For that, we have to consider all the forces acting on this footing on one side, either left side or the right hand side. And considering the lever arm to be at a distance calculated from this critical edge, we have to calculate the moments of all the forces acting on one side, and that bending moment will be the critical moment for that critical section. The greatest bending moment to be used in the design of an isolated concrete footing which supports a column, pedestal, or wall shall be the moment computed in the manner prescribed in 34.2.3.1 its sections located as follows. So this clause 34.2.3.2 says us about the plane of the critical moment, which we have already seen here. If you look at this number A itself, this critical phase or this critical section is at the face of the column for footing supported on a concrete column. And finally, in clause 34.3.1, we have total tensile reinforcement shall be distributed across the corresponding resisting section as given below. In one-way reinforced footing, the reinforcement extending in each direction shall be distributed uniformly across the full width of the footing. In two-way reinforced square footing, the reinforcement extending in each direction shall be distributed uniformly across the full width of the footing. This is in the case of circular footings. Sorry, not circular, square footings. If our footings are square, then the reinforcement which is derived from the bending moment considerations are distributed uniformly across each length of or width of the footing. That means along each dimension of the footing. But if our footing is of rectangular type, then primarily there are three zones. We have two end zones and we have one mid zone. In mid zone, our reinforcements are spaced closely apart, while in our end zone, they are spaced a little further apart. So this is the distribution of tensile reinforcement in our footings, and this clause 34.3.1 ABC also talks about the same. You can read this clause C on your own and see how this describes the reinforcement distribution in the case of our rectangular footings. So I will leave this to your own reading. And providing development length, we all know the concept of development length. In the case of footings also, the development length and the design bond strength is the same as that in beams and slab. Is in our clause 26.2.1, we calculate the development length based on this same formula. You can go this formula or you can go through this formula on your own. And in clause 34.2.4.3, the critical section for checking the development length in a footing shall be assumed at the same planes as those described for bending moment. That means along the face of the column is where we also have to check for our development length. And if there is an abrupt change in the section of our footings, then in that places also we have to check for development length. And also in sections where our reinforcement is curtailed, the anchorage requirement shall be checked in accordance with this clause. So this is about development length. I did not go through this in very detail. We all know the concept of this. And finally, when designing our footings, one thing that we have to check for is the transfer of load at the base of column. That means we have to transfer our load from column to our footings. How do we check for transfer of load at the base of column? So what types of load can exist on a column? There may be axial load, there may be shearing forces, or there may be moments. All those forces that are coming onto our columns shall be transferred properly to our footings. So the axial loads, moment and shear acting at the base of a column or pedestal are transferred to the footing by any one of three means. And those three means are, in number one, compressive forces are transferred by bearing on concrete surface as well as by reinforcement. The tensile forces due to moment and by reinforcement bar, which are properly anchored into column as well as footing with adequate development length. And finally, our lateral forces are transferred by shear friction or shear keys. So all the three types of forces, axial load, moment and shear acting at the base of a column should be transferred to our footings, and there are various mechanisms through which those forces are transferred. But in the case of our codal provision, our code only talks about the transfer of compressive stress. So let's look at this. The compressive stress in concrete at the base of a column or pedestal shall be considered as being transferred by bearing to the top of the supporting pedestal or footing, and the bearing pressure on the loaded area shall not exceed the permissible bearing stress. This permissible bearing stress means, in the case of limit state design, 0.45 FCK. So the bearing pressure should not exceed this bearing stress multiplied by root under A1 by A2. Root under A1 by A2. A1 and A2 into A1 by A2 root under into 0.45 into FCK. The bearing pressure should not exceed the value of this factor. So what is A1 and A2? A1 means the area of the supporting surface, and that supporting surface should be geometrically similar to and concentric with the loaded area. And A2 means the loaded area at the column base, or the actual bearing area of the column. So our bearing pressure means 0.45 root under FCK for limit state method. We already have talked about this. So where the permissible bearing stress on the concrete in the supporting or supported member would be exceeded, reinforcement shall be provided for developing the excess force. And that reinforcement can be either done by extending the longitudinal bars in the supporting member, as we have seen in the second figure, or by the use of dowel bars. So if the permissible bearing stress due to the loads acting on this column is greater than the bearing stress, then for additional forces, some reinforcement has to be used to transfer the load, and that reinforcement can be either through the use of dowel bars or by extending the bars of the column into the footing itself. Where transfer of force is accomplished by reinforcement, the development length of the reinforcement shall be sufficient to transfer the compression or tension to the supporting member in accordance with 26.2. We have already seen about the condition of development length, and this 34.4.3 and 34.4.4, you can look at these codal provisions by yourself. It is not needed much during our analysis and design of these foundations. So to determine the value of A1 and A2, we can see here our A2 is the bearing area, that is means the area of this column, and to determine the A1 area, we can draw this line from our loaded surface or from our loaded area in the ratio of 2:1. You can start a line here and we draw a horizontal, or we draw a slanted line which is increasing at the rate of 2:1, 2:1 in both sides, and after one side meets the edge of this footing, and that means it may meet on this side or this side, draw a horizontal line from here, and A1 is measured on this plane. If we see in plan view, A1 is measured here. This is the value of A1. So this gives A1 and this gives A2. So root under A1 by A2. So we have come to the end of this design, foundation design. We saw some general considerations only today, and since our lecture has already extended to 35 or 40 minutes, we will see at the design of our footings in Excel sheet by considering the design reactions that we extract from ETABS in our next lecture, and also we see the design of our footing in our SAFE software. So let me allow to end this presentation for today. We will meet again soon. Thank you.